welcome back. Today I thought I would show a quick design example of a current reference that is generated using a threshold voltage. If we take a current mirror and put a diode NFET underneath it like this, and add a resistor underneath the other FET, we can generate that current. If we follow the loop here, we are going to increase a VGS1, and then we increase a VGS2, and then we drop back down a VGS3. And then we have R here. So to generate this current, we need to decide how we plan on sizing these devices. If we size VGS1 as a unit device and VGS2 as that same unit device, then we need to figure out how to size VGS3. But in order to do that, let's work through the expression real quick. So we have VGS1 plus VGS2 minus VGS3 is equal to VR. And to break that down a little bit further, that is V threshold plus VOV1 plus V threshold plus VOV2 minus V threshold minus VOV3. Now we need to size VOV3 such that VOV1 plus VOV2 is equal to VOV3. But given that we know the current that is flowing through M1 and M2 is the same, and the aspect ratio is the same, we know that this quantity is the same. So this is 2 VOV is equal to VOV3. I'll call that VOV1. And essentially what this tells us is if we look at the equation for overdrive, it's 2ID over K prime W over L square root. We need to bring a factor of 2 out of here, and in order to do that, the W over L needs to be a quarter, and that's how we size that output FET. So if we size that at a quarter, then what we get is 2ID over K prime W over L times a quarter square root. That goes out into the numerator, and then we get the 2 VOV. So now, if we plug that back into this expression, we have VTH plus VOV1 plus VTH plus VOV1 minus the threshold minus 2 VOV1. And pretty much everything's going to start canceling out except for that first threshold term. So we have imposed the threshold voltage on R, and as a result we can define the output current as VTH divided by R. To summarize the example that we just covered, the output current is equal to the threshold voltage divided by the resistance. Now, if we were to take the partial derivative with respect to temperature, then we're making an assumption that the temperature coefficient of that resistor is 0, that it does not vary with temperature. The partial derivative of threshold with respect to temperature is going to be less than 0, and what this tells us is that it is complementary to absolute temperature, or CTAT. And all that's saying is that as your temperature is increasing, your threshold voltage is decreasing. And as a result, that means your current will be decreasing. Now, I want to show you an example of a current reference that would be PTAT, or proportional to absolute temperature. Now, if we take an NFET and we make a current mirror that has a very large W over L, then we would be purposely putting this current mirror into subthreshold, provided that the input bias current is low enough to do so. Now, from what I've drawn here, we have a resistor in the second branch, and M1, M2 are labeled there. If we have a 1 to N ratio here, let's derive the output current now. In subthreshold, the drain current equation is roughly going to be equal to some scale factor, I0, W over L, exponential of VGS over phi t. And if we rearrange this expression for VGS, then what we get is the phi t natural log of ID over I0 times that W over L. Now, if we go back to KVL, if we go up a VGS on this first vet and then down a VGS2 on the second vet, that delta is what is going to be the VR voltage. So VR here is going to be a VGS1 minus a VGS2. And using the expression that we just calculated, what this works out to be is phi t natural log of ID over I sat W over L minus phi t natural log ID over I0 times N W over L. And one of the properties of natural logs is that if you subtract them, then what we can do is we can divide them. So what this works out to be is phi t natural log of N. So this VR is equal to that. So the output current is now equal to VR over R, which is just phi t natural log of N over R. And that is what the current is for this current reference. Now, again, if we were to take the partial derivative with respect to temperature of I, then what we'll find is that we have a temperature dependence in phi t, which is proportional to temperature, meaning that this derivative of I is going to be greater than 0, or it would be proportional to absolute temperature. To show you another interesting example, we could take the first and second current mirrors that we just went through, and we can combine them to some degree. So if we were to take, I'm going to go back to black. If we take the first current mirror that we put together, call this IN. This is the first current mirror that we had. So this is R. Now if we were to grab the second the second current mirror, what we could do is actually utilize this diode structure here. Oops, sorry. Put a resistor here. So this is going to be R1 now. This will be R2. 1, 1, quarter, as we just derived, and then this is N. So we have the two different currents, and now what we could do is sum the two of them up together, and this would be I out. And the expression that we would get here is that I out is equal to VTH over R1 plus phi t natural log of N over R2. And to take this a step further, if we take the partial derivative with respect to temperature of I0 and then set that equal to 0 to optimize for a flat temperature coefficient, if this is 0, then that's typically called ZTC, zero temperature coefficient. This would be equal to 1 over R1 dVTH dVT plus natural log of N over R2 d phi t dt. And the reason I brought this first term and this second term out is because they have no temperature dependence. They're just essentially multiplying whatever the derivative of those other two parameters are. And the phi t is a known quantity, the derivative of that is, and the thermal voltage, I'm sorry, the threshold voltage tends to be around minus 1.4 to minus 2 millivolts per degree C. But to get something a little bit more precise, you probably want to simulate this and get a more accurate number. And what you can do is rearrange these expressions and solve for a ratio of R2 over R1, and that'll be something that's probably close to. I'm just gonna make a guess here that R2 over R1 is probably going to be close to 15 or so, and that'll give you the relative ratio for R1 to R2, and then from there you also know what output current you're trying to target, so you can use that as your second expression, and with those two expressions you can derive an output current that is that's ZTC, or flat with respect to temperature. And if we were going to graphically show what we just did in a plot, we have I versus temperature. We have a PTAT. Oops. So we have PTAT here. And then we have a CTAT component here. And by setting these ratios of N, R1 and R2, we're tuning these slopes, and ultimately we're going to sum up those currents and get something that's nearly flat with temperature. It's not going to be perfectly flat. There's going to be a little bit of a curvature due to higher order effects, but it would look something like that. And you could get a pretty solid current this way without having to generate it from some sort of architecture that's feedback loop based, such as like a beta multiplier reference.